Salutations and fist bumps, folks. Welcome back to the Coding Shield. If you're new here, this channel is about learning together, building the foundations, while also documenting my own journey into quant finance and cybersecurity with a twist or co-combined somehow. But basically what I'm trying to say is this is a way to document my journey into quant finance and in some regards cybersecurity as well, because that has to be secure. And I know that's probably something that you're not necessarily expecting from a coding channel, but again, this is a way to learn with you while also teaching what I do learn myself and documenting the journey along the way. But we're also not just coding things just to make sure that they work. We're also going to dig deep and understand why they actually do. So today we're going to start a new series that I like to call the Foundations that is actually going to be inspired by the Data Structures the Fun Way book. And as you might expect, we're starting where everything kind of begins, how computers actually store data. So if you want to work in AI, quant finance, or cybersecurity, you want to listen up here because everything kind of hinges on this stuff. Now, let's start with the very basic units of storage. Variables. Variable, contrary to what you might think, is not necessarily a black box. It does have physical properties inside of your computer. But a variable, as it's called, is a name that points to a specific location inside of your computer's memory. For better example, think of your computer's memory as a row of lockers. Each locker is assigned to a specific person and has a specific address. So if I were to write in Python, gems_locker equals 109, what I'm effectively doing here is not necessarily just creating a value. I'm also creating space inside of the computer's memory to say store 109 as gem_locker. Why does this actually matter? Memory size and type matter a lot. An integer might take up one memory slot, a floating point number might take one or more, and a Boolean might take almost nothing. This is why types in programming languages exist, specifically in stuff like C++, C, Rust. There's things that you have to actually specify. But in Python, it's more implicit. As a quant finance side note here, floating point precision errors are real money problems. And as a cybersecurity insight here, memory layout mistakes are often how buffer overflows happen. So understanding how these things are actually stored inside of your computer matters a lot. Now, just because you can write anything in terms of the name of your variables doesn't mean that you actually should, because clean variable names equal clean thinking, especially later on. You're going to thank yourself 6 months down the line to a year if you do this. Some examples of bad variable names would be stuff, temp, or x1, or just something like a plain single number or letter like D or 1. Like I said earlier, your future self and your teammates will thank you immensely, because bad variable names aren't just messy, it can be a cognitive security vulnerability or just a hindrance to production flow, which both of those things are catastrophically horrible in terms of actually getting the job done. But I would be remiss if I didn't actually tell you that you can put data structures together, specifically if you want to house more than one thing, and that would be a composite data structure, or something known as an object or something known as a dictionary in Python, an object in JavaScript, or a struct in other languages. Most often, real programs don't actually use siloed or isolated data. They more often use related data or groups of data that we then use or make useful inside of some type of program or inside of a user interface. A perfect example of this would be a comic record or a coffee record or something like that. And in Python, this could be, again, a dictionary, a class, or a data class, a struct, or whatever the actual language decides to call it. But then why does this actually matter? Well, because passing one object is safer than passing 6 loose variables, and bundling related data reduces accidental leaks. If you're thinking about this from a quant insight, market data, timestamps, prices, and metadata should travel together, because oftentimes that actually tells you some signals on what you should and should not buy. All in all, to enforce data integrity, you want to use a composite data structure. Speaking of composite data structures, let's talk about one of the more basic ones, which would be arrays. Now, if you've never heard of an array before, an array is a continuous memory, equal-sized elements accessed by index, not name, inside of your computer's memory. And this is why arrays are fast in general, at least until they aren't. We'll get into that part a little bit later in the video. Now, for example, if we had prices, for example, inside of an array of in size, we would then index or find the specific prices for specific stock indexes or stock prices inside the array by indexing into that particular base of memory. And most programming languages start indexing by 0. So if we were indexing for the first price, we would do prices bracket 0. And this is also because memory addresses usually start at 0 as well. So this lets the computer calculate memory address equals base address plus an index and the element size. For a trivial example of what's going on under the hood. If you're looking at this from a quant perspective, this is why vectorized operations are so fast. And if you're looking at this from a security standpoint, out-of-bound access could actually be a territory for exploitation. Now, like I said, it's easy to find things inside of an array, pretty easy, as long as you are able to index for a specific thing. But what if you have to go if we go back to our lockers example, what if you're looking for locker 126 down the entirety of a hallway? You probably don't want to go 1, 2, 3, 4 all the way down the hallway until you get to locker 126. You might want to actually do a little bit more of a elegant search. And we can do this with arrays a little bit easier with some algorithms. You can do stuff like this with arrays, and most of the time, the way that you do this will be attached to an algorithm. For an example, we're going to look at insertion sort and see how arrays actually are put to work. So, insertion sort takes advantage of indexing to gradually sort our data. The idea for this particular algorithm that you want to keep in mind is that the entire thing could be unsorted, or one side could be sorted, or the left side could be sorted, or the left side of the array could be sorted, or the right side of the array could be sorted. And if if everything is sorted, then we're already done. But this allows us to take one value and shift others to make space. But this also teaches us that arrays aren't necessarily that flexible, because to insert something, you must shift values one by one manually. This is why insertion sort is known to have a big O notation of O n squared, which is in the very worst case. So what does that actually mean in practice? Small data sets, wonderful. This would work fine in terms of putting everything inside of an array, and you're all good to go. Large data sets, especially if you're talking about quant data sets, that's going to take a long time, and time is usually always of the essence when you're talking about quant finance, at least from what I've gathered so far. Now, the last thing that I want to talk about in this video are strings. Strings are a type of an array that seem like they're very magical, but they're not. What they actually are just arrays of characters. What's happening under the hood is your computer is storing all of those characters in individual places inside of a block of memory for an array. And then once we get to the end of that, usually denoted by a slash, then we say, hey, that's completely done. We're all good. There's nothing else that we need to add here. If we then want to compare that, again, let's say, for example, we have password and input password as the variable, then we would compare the strings compare the characters one by one, from left to right until a mismatch is found, or until we get to the end of the actual values. Variables, objects, arrays, strings, all that kind of stuff is not exciting at all, I know. But it is very foundational to understand how they actually work inside of the programming language that you're running, because that's going to be your superpower, especially in the age of AI and all that kind of stuff. If you understand how the underlying things work, it makes you way more powerful, especially if you're going to use AI to do some leveraging things to make your time a little bit more feasible. But every advanced structure, hash tables, trees, graphs, all that kind of stuff, and AI in general is built on these ideas, even down to the very granular things when you're talking about large language models and all that kind of stuff. It boils down to this. Where are we storing our data? How are we storing it? And how fast can we get access to it? If you didn't master these fundamentals, and specifically memory fundamentals, Python becomes clearer, algorithms become a lot more predictable to understand, and performance becomes intentional. So if you like this video and if you like content like this, go ahead and hit that like button and share this with a friend. And if you'd like to stay around for the entire journey of my quant exploration, go ahead and hit subscribe. And until next time, y'all be smooth. Blur it out.